the real life application ng tinatawag natin weir. Ito, rectangular weir. Okay? So, although meron na marami ng mga leakage dito, pero this is a type of a rectangular weir used for irrigation canal.
Now, let us demonstrate the application of the engineering concept of rectangular weir or throw in solving problems involving calculus. What was shown in the video is an example of throw with rectangular cross-section. We shall illustrate application of calculus concepts in solving the worded problem. However, we are to replace the cross-section with a triangular throw, which is 3 meters long, 2 meters wide at the top, and 2 meters deep. Assuming water flow at the rate 2 cubic meter per minute, we are going to find how fast the surface is rising when the water is 0.5 meters deep. Now, let us identify the given data based on the worded problem provided. The properties of the triangular throw was provided. Length is 3 meters, width is 2 meters, and height is 2 meters. Okay, so we are now going to draw the triangular throw. According to the problem, we have a triangular throw. So we are going to identify the different properties of the throw that was described in the problem. So we have a triangular throw. Okay, so let me just represent it. By the way, I am drawing not to scale, just to illustrate how the triangular throw and the water inside it is illustrated. Okay. So we are going to illustrate the water inside it. Okay. So that is the triangular throw. And if you are going to notice, according to the problem, the length of the triangular throw is 3 meters. And the width at the top is 2 meters. So the width at the top of the triangular throw is 3 meters. Sorry, 2 meters, I mean. That is a 2 meter wide. So the width of the triangular throw is 2 meters. And also the triangular throw has a height of 2 meters also. Yeah, that's according to the problem. And the water is at a depth of 0.5 meters. So the depth of the water is at 0.5 meters. And then we are also given, if you are going to draw the cross section of the triangular throw, so this most likely be the illustration of the triangular throw. So the water is at a depth of 0.5 meters. Let's say we represent it by small letter h. And then of course, the triangular throw has a height of 2 meters. It's also 2 meters. And the width is also 2 meters. So this is 2 meters. And then of course the length is given, which is 3 meters. And we are going to use this value. Let's say we represent this to be x, while we represent the height, this as the height of the water. So we are going to find how fast the surface is rising when the water is at 0.5 meters. So we can represent the variables in terms of x and in terms of y. Aside from the dimensions of the triangular trough, the volume is given 2 cubic meters per minute, and the height of the water is 0.5 meters. Once you have identified the given data, it is about time to identify what is being asked in the problem. From the known variables and the data being asked in the problem, we shall find the most appropriate formula. The formula suited to solve for the unknown variable. In this case, the formula for the volume of the triangular trough may be used. The volume of the triangular trough may be determined by multiplying its cross-sectional area by its length. Thus, the volume is equals to 1/2 times x times y times the length, where x and y represent the width at the top of the water level and y is the height of the water level, respectively. Now, by ratio and proportion, we may say that x is to y as 2 is to 2, where again, x and y represent the width at the top of the water level and y represent the height of the water level, respectively. Thus, x divided by y is equals to 2, which is the width at the top of the triangular trough, divided by 2, which is the depth of the triangular trough, respectively. Thus, by mathematical operation, we can arrive at the equation that x divided by y is equals to 1. And that means x is also equals to y. It follows that upon substituting in the equation for the volume, v is now equals to 3/2 times x times y. The volume 3/2 times x times y will now become v is equals to 3/2 times y times y. It certainly follows that the volume is equals to 3/2 multiplied by y squared. Now, applying differentiation, we will arrive at the equation dv over dt, or the change in volume with respect to the change in time, is equals to 3/2 times 2 times y times dy over dt, or the change in y with respect to the change in time. Thus, dv over dt is equals to 3y times dy over dt. And since the change in volume with respect to the change in time, according to the given data in the problem, is 2 cubic meters per minute at the instance where the depth of the water is at 0.5 meters. Therefore, it follows that 2 is equals to 1.5 times dy over dt. Thus, dy over dt is equals to 2 divided by 1.5. Leads us to the answer in the question. How fast is the water rising or the water surface rising, which yields to a value of 1.33 meters per minute. That means the water surface is rising at 1.33 meters per minute. That is our answer to the question.
See you on my next vlog. Bye-bye.